Good evening everyone. Today I have planned to revise the electric flux concept with you. The electric flux is the totality of number of lines of forces passing through a surface, and electric field in a region gives you the actual estimate of number of lines of forces passing through a unit surface placed at the point if the surface is kept in a direction normal to the direction of flow of the lines of forces. And before starting this topic, I will assume that electric field you have revised, as the concept of electric field is required, and the modified definition of electric field in terms of electric lines of forces. That is just what I have told. I repeat again. It is electric field at a point is the number of lines of forces passing through an unit area held at the point in a direction normal to the direction of lines of forces to the point. So it is number of lines of forces passing through an unit area. If the area is taken in a direction normal to the flow. Now, if I take a surface this manner and want to calculate the number of number of lines of forces passing through it through a small area, then we should remember the definition of electric field, that number of lines of forces passing through an unit area held at the point. This is area vector. Sometimes area in physics is considered as a vector quantity. The area vector will be directed in a direction normal to the area. So if this area, this small area, is of length ds and unit vector assigned to it is along n cap, then one can write area vector ds is equal to ds, the magnitude of the area, multiplied by n cap. This is the presentation of area vector. Now, suppose electric field in this region directed this way, E. The angle between these two directions is equal to theta. These two directions means the direction of n cap, and the direction of n cap is the direction unit normal drawn to the area. This is the small portion of the total area vector normal to it. We are going to calculate electric flux through the whole area. To the small area, to find the electric flux, we write d phi. Phi sign is used for electric flux. D phi is going to be equal to the component of electric field vector along n cap, that is E cos theta into ds. By using vector sign, this can be written as E dot ds. Okay. E cos theta is the component of electric field along n cap, and then d phi will be E dot ds electric field vector normal and ds vector is of the electric field vector going this way and area vector is normal to the area, so d phi is the measurement of this. So why it is like that? Because by definition it is number of lines of forces passing through unit area, unit direction normal. If the field is going this way, normal going this way, then electric field vector normal to the area will be this manner. Per unit area, electric lines of forces passing through is given by E cos theta, because component of E in this direction E cos theta. So over this area it will be multiplied by dx. So over the whole surface if you want to find, then electric flux through the whole surface, electric flux to the whole surface is given by phi equal to integration E dot ds over the surface. This is taken as s. It is not necessary to take s over there, but it means over the whole surface. Actually, there is use of double integration here. We avoid it just by writing this. Will not bring the double integration into consideration. So over the whole surface it is E dot ds. Now several cases will arise. We will discuss one by one how to calculate electric flux. Right now we are going to consider 4 cases one by one. Case 1. Let us find electric flux if we keep an area this manner, which is normal to the direction of lines of forces. So this area here, area vector is directed in this direction only. Electric field vector directed this way. So case 1 is going to be the case where unit normal in cap also has the same direction. Case 1 is when E is perpendicular to the given area. That is, this is normal to the area, electric field also normal. That is, angle between E and n cap is equal to 0. So in this case, phi through this surface will be what? Just through unit area it is A. Over the whole area, if the area is taken as A, phi is going to be equal to E into A. Okay? So this is one case. If the area is kept normal, if we consider another one, if the electric field directed this manner and the area taken this way, circular region, this area is A, n cap and area vector same direction. In this case also, phi is equal to E into A, because n cap and area vector in the same direction. So simply multiply it, because per unit area E over the whole area A, it will be E into A. Case 2. Case 2 is the case when the area kept this manner. So in this case, if I draw, I cannot draw it actually. This area vector this manner and electric lines of forces going this way. So here, this is the case when theta equal to 90 degree. E and n cap perpendicular to n. E and n cap are perpendicular to each other. So this time flux through the surface is going to be phi equal to E A cos 90 degree. This is equal to 0. Okay. Now, if we consider circular area this manner, in that case also phi will be equal to, here area vector directed this manner coming out in cap. So here also phi equal to E A cos 90 degree. That is equal to 0. Now a question arises, a numerical problem. If I ask you the square of side length A is kept this manner and the charge Q is kept here. What is the flux through the surface? This is the square of side length A. What will be the flux through the surface? Find phi through the square plate. In this case, lines of forces, you will see that directed in all directions, they are coming this way and parallel. Coming this way means the charge from the charge only, no, not from here. So from here, if it goes this manner, or goes this manner, or this manner, then lines of forces are going. So you have to answer this way: lines of forces due to plus Q are either parallel to the plane or perpendicular to it, isn't it? When it is parallel, lines of forces going this manner or this manner. In first case, means parallel to the plane, In the first case, E and n cap we have taken for normal drawn to the surface under consideration. E perpendicular to n cap, so phi equal to 0. In second case, no E, no lines of force, no lines of forces will pass perpendicular to the plane. Am I correct? Because lines of forces will go this manner only. It will not be extended here because charge is situated here. So in this case also, phi, if you take phi 1, this phi 2 equal to 0. So total flux through the surface, phi equal to phi 1 plus phi 2 will be equal to 0. Okay. So second case we did, and one example we did where the concept is based on both when theta 0 degree, theta 90 degree. Now the next case, flux through a closed surface. This you take case 3. Electric flux through a closed surface. Electric flux through a closed surface. We assume that there is a sphere and at the center a charge Q is kept. Our problem is to calculate total flux through this closed surface. We want to find, this is a sphere, not a circle. Okay? We want to find radius of the sphere. We want to find total flux linkage through this surface. How to? Just this is a sphere of radius r. We imagine if this charge Q is exactly at the center, we imagine a small area ds on the surface. Okay? Now electric field will be directed this manner and area vector and in unit normal is also directed this manner in cap. So flux through this surface d phi, and you know this E has a measurement Q by 4 pi E0 r square, directed normal to any point on the surface of this sphere. This one is a sphere of radius r. So d phi will be equal to E into ds cos 0 degree. Why? Since E parallel to n cap. So d phi equal to EDS phi over the whole surface will be, and by symmetry E has same value, the measurement of P will remain the same everywhere, so E will come outside ds. So phi equal to E into over the whole surface. If you take integration, it will be 4 pi r square. Okay. Now what is the value of E? Q by 4 pi 0 r square, 4 pi r square. So this is Q by E0. So if you charge Q is enclosed, in fact this is the statement of Gauss theorem. Application of Gauss theorem to this topic will be done in the next video. There, in fact, for any closed surface, we'll know that the flux coming out is given by Q by E0. Okay? And this through a closed surface, if we keep any closed surface here, total outward flux, I mean total number of lines of forces passing through the surface, will be Q by E0. This is considered as case 3, but actually the case when E and n cap are parallel or directly in the same direction. Case 4. Case 4 is the case where we are going to find flux through arbitrary cases. Like suppose there is a sphere. No, don't take sphere, it will be a bit complicated one. We want to find flux linkage through this circle area. through this circle area where a charged thread is kept, this one charged. Charge thread is kept this manner, end is at the center, it has line density of charge lambda equal to line density of charge. What will be the electric flux through this circle area whose radius is r? How to find? For a long straight wire at the extremity, you have done it before, at a distance r, the electric field has both the components there, along x-axis, along y-axis. This distance be r, line density lambda, electric field is lambda by 4 pi 0 r this manner, y equal to lambda by 4 pi 0 r in this. So resultant field was like this, ER equal to, this we have done by integration before, this root 2, as these two are equal, this is 45 degree, this one 45. So what will be the flux through this surface, this circle area? What we have to do here first, we find the flux through this circular area first. This is the circle area, this has radius r and thickness dr. Okay, I am not describing it. This one r, this is overwriting not possible. This one r, this one dr. This dr is the thickness of this circular part. So through this circular area, we will find electric flux through this small circular area, and then by integration for the whole thing. Let me see how to find. I draw a bigger diagram for you. So this is the case where electric field is neither parallel nor perpendicular, and this is not a closed surface, it's a circular area. Circular area, it has radius r. To find the flux through it, we have taken, what did you take here? We have taken elementary area through this point. This has radius r and thickness dr. So according to our discussion, this is dr. Electric field here has two components, along x-axis as well as along y-axis. Resultant is ER, this is 45, this is 45. What is the area of this portion? If radius is r, then area of this part is 2 pi r into dr. So flux through this area will be not due to Ex, through this small area, EX has no contribution. Why? Because it is going parallel to the circle area. Only EY matters. So defy flux through that small portion will be electric flux through the elementary part is equal to EY into 2 pi r dr. EY is what? Lambda by 4 pi E0 r. So this is nothing but r are getting cancelled. So it is very interesting to note that this part has become a constant. Therefore, total flux is integration of this thing. Lambda by 2 E0 will come out, and this will integrate from 0 to r, that is r. So phi is equal to lambda r by 2 E0. So this circle. Another problem of this category is better to discuss with you, where a charge Q is kept in front of this circular region. This charge Q is kept. This has radius r. What is the flux through this surface? How to find it? Again, the same manner, we consider an elementary part here like this of the circle area. This one r and thickness dr. Then we will get it by integration. Now, at this point, if you consider the electric field due to this charge plus two lines of forces are going in all directions, here E will be directed this way. If the E vector makes an angle theta with the horizontal, then component this way, normal to the area, this area, normal to this area will be how much? It has two components, E cos theta this way and E sin theta this way. Again, E sin theta has no contribution, only E cos theta. So d phi will be this distance they have given. Suppose this distance is L and this radius is r. So it is 2 pi r into dr, the same manner, into E cos theta. What is the value of E here? Where E is going to be Q by 4 pi E0 r square plus L square. Because this distance r dash is equal to root over L square plus r square. Q by 4 pi r square, I took that only. So you substitute here 2 pi r into Q by 4 pi E0 r square plus L square into cos theta. What is the value of cos theta here? This one theta, this one is also theta. Cos theta is going to be L by r square plus L square. So this is nothing but 2 pi get cancelled. QL by 2E0, dr factor is there. Q into L by 2E0, 2 pi get 4 pi get cancelled, 2 is remaining. R square plus L square to the power 3 by 2 into dr. R is also there. So to calculate total flux, we should integrate it. So flux through the surface will be integration of d phi, that is QL R dr by R square plus L square to the power 3 by 2. You will integrate it from 0 to R. For integration, put R square plus L square equal to Y square. Show R dr equal to Y dy. Two is 0. Now change the limit here when R equal to 0, Y equal to L, R equal to R, Y equal to R. So this is 0 to R. R dr is Y dy, substitute by Y cube. This is dy by y square minus 1 by y is the integration. This will be, so this is L. This will be L2 into her, and that upper limit to lower limit will give you 1 by L plus 1 by, this is the thing. Okay, there will be minus. If you take L inside, so phi going to be Q by 2E0 1 minus L by into her You try at home to get the flux to this circle area if another charge minus Q is kept here. Okay? How to find flux through this circle area if another charge minus Q is kept over there. Okay, see you again coming back with the application of Gauss theorem for the calculation of electric flux, and the concept of solid angle also we are going to learn in the next video. I think Gauss theorem simple applications you are familiar. You all know that is electric field due to a long straight wire, electric field due to plane sheet of charge. Where you find direct application of Gauss theorem? Definitely I am not going to discuss direct application. I will be discussing the case which will be a bit which will give you a bit trouble to think. Okay, see you again. Thank you all.